Okay, so we immediately go on with the next presentation, which is going to be by Ki. Good. So, she will be talking about environmental effects and biaxially oriented PMMA. The floor is yours.
Thank you. Hello everyone, my name is Christine and I'm from Imperial College London. My presentation today is on the environmental effects in biaxially orientated polymethyl methacrylic, PMMA. Here is the outline of my presentation. We'll go through the introduction, aims and objectives, then experimental, results and discussion, and finally the conclusion. PMMA is a lightweight alternative to glass and a cost-effective substitution for PC aircraft canopies. One recent development is amorphous PMMA used in aircrafts are often biaxially stretched, pre-stretched, to force the polymer chain to adopt an ordered arrangement in the direction of applied stretch. The resultant biaxially orientated PMMA has improved toughness, crack resistance, impact resistance, fatigue performance, and anti-crazing properties. The aims and objectives of the project are as follows: to stimulate crazing defects an aircraft canopy may encounter during its service life, to investigate the fracture mechanism and crack growth in both air and environment using a fracture mechanics approach, obtain time for crack initiation, crack speed, and their corresponding fracture toughness for the materials, compare environmental stress cracking, ESC resistance, of each material in order to predict component life expectancy. Two different grades of PMMA were used. The amorphous PMMA used were 5mm clear acrylic sheets sourced from RS Component Limited. The biaxially stretched PMMA used were 7mm YBDM10 provided by BM. The manufacturing process consists of clamping the four edges of a sheet of amorphous PMMA and pre-stretching it simultaneously in both in-plane direction at an elevated temperature. The resultant mean orientation degree, lambda, is roughly 70%. So here are the characterization tests I did. Uniaxial tensile tests were done to calculate the tensile modulus and tensile strength of the polymers. Dual cantilever dynamic mechanical analysis, DMA, tests were used to determine the glass transition temperature. 3-point bending tests were performed on single-edge notch bending SEMB specimens, which is this here, to determine the fracture properties. Specimens were tested at a displacement rate of 10 mm per minute. A pre-crack was created by broaching from a machined V-notch to ensure a sharp crack tip prior to testing. An optical microscope was used to observe the notch tip radius of each pre-crack after broaching. This is to ensure a sharp pre-crack and to avoid any crack tip greater than the material crack opening displacement in the specimen used for testing. And lastly, SEM were used to investigate the microstructure and identify crazing mechanism from the fracture surfaces. So the broaching method. Sharp pre-cracks were introduced by broaching. Broaching is a cutting method where materials are removed during each crack. As you can see, this is the motion of the blade. And this was achieved by using a custom-built rig with a modified knife blade, as you can see in this figure. So broaching is important because it is to ensure a sharp notch tip radius and a constant notch depth across the thickness of the specimen. And lastly, to eliminate any residual stress that might be introduced from the conventional razor tapping method. Environmental stress cracking tests were performed in both air and methanol to hasten crazing on PMMA. SEMB specimens were tested under load control. A constant predefined load, hence constant G, was applied gradually to the specimen to prevent crack tip blunting from shock loading. Time and voltage data measured from a LVDT were used to calculate the crack initiation time and crack speed. An LEFM approach was employed to investigate the crack initiation and propagation during ESC. The compliance model, this one was used, where C is the compliance, delta is the displacement, and P is the applied load. E is the Young's modulus, B is the specimen thickness, and X is the normalized crack length against specimen width. The bending and shear contribution is expressed by the first term in the square bracket, which is 9/8, and the second term accounts for the presence of crack tip and growth. The geometry factor Y of an SEMB specimen under 3-point bending condition can be expressed as follows. The compliance of a blunt notch specimen can also be found using the same specimen model. So the point of crack initiation can be defined when the compliance ratio between a sharp and a blunt notch specimen differ by 2%, which is roughly at this point on the graph. And by rearranging the compliance equation, an instantaneous modulus E can be found, and by substituting E into the equation below, the instantaneous fracture toughness throughout the test can be determined, where GC is the fracture energy and KC is the fracture toughness. Here we have the material properties of both polymers. The biaxial orientation has greatly improved the material fracture properties from its amorphous form. The increase in tensile strength from amorphous to biaxial PMMA is due to the increase in chain alignment in the direction of stretch. The decrease in tensile modulus after the biaxial stretching process can be explained by the high ductility in the biaxial materials. In other words, at a given stress, the BOPMMA can withstand a higher degree of deformation, hence experiences a higher strain compared to the amorphous PMMA. The glass transition temperature are similar in both material, as the stretching process does not alter the chemical bonds within the material. The fracture properties of PMMA were enhanced with the 70% orientation degree, and this is reflected through the KC and GC values. Both polymers have passed the 3 LEFM validity checks stated in the ISO standard. The crazing mechanism. Crazing often nucleates from inherent defects in the material, resulting voids or interspace with fibrils. When applied with sufficient energy normal to the plane of crazing, the adjacent fibrils separate, forming a crack. The fracture process experienced in ESC can be explained by the relaxation growth model. 3 distinct regions, labeled region 1, 2, and 3, can be found on the log G and log crack speed curve. When the specimen is first loaded in region 1, the crack propagates slowly, allowing enough time for the environment to flow and submerge the crack tip. Hence, the fracture toughness of the materials is independent to crack speed. In contrast, during the fast crack growth observed in region 3, the environment does not reach the crack tip. Thus, the crack growth in this region is identical to those in air behavior. Region 2 is the flow control transition region, whereby the energy required to create 2 new fracture surfaces is reduced in the presence of environment and becomes limited by its availability. And depending on the model applied, this transition slope has a gradient of either 0.5 or infinity, which correspond to constant speed. Here we have the ESC initiation plot for both amorphous and BOPMMA. On the x-axis, we have time, and on the y-axis, we have fracture energy. On the left, we have amorphous PMMA, and on the right, we have biaxial orientated PMMA. The in-air points are hollow points, and the in methanol are solid dots. On both plots, one value of initiation time was obtained from each successful experiment. Thus, each point in the initiation plot represents one single test. The intersection of the in-air and in-environment curves, which is this point, represent the intersection of the in-air and environment represent the value of critical initiation time and their corresponding fracture energy. Overall, at least 5 repeats were performed on both materials under each environment, except for the case of biaxial orientated PMMA in air. Only one complete set of data was obtained, as the environment has a high ESC resistance, and often the crack does not propagate through under constant load. The crack bunting effect may dominate at high crack speed, resulting a crack tip radius exceeding a critical value. As a result, the crack growth will pause under constant load condition unless more energy is applied to propagate the crack. And as suggested from the amorphous PMMA result, the initial load and therefore the initial fracture energy applied to the specimen in methanol are significantly lower than those performed in air. Here we have the ESC propagation plots for both amorphous and biaxial PMMA. And on the x-axis, we have crack speed, and on the y-axis, we have fracture energy. The intersection points of in-air and in-environment curve indicate the value of critical crack speed and the corresponding fracture energy. Once the crack is initiated, the energy required to propagate the crack in methanol is lower than in air until it becomes flow controlled. Above this critical point, the availability of the environment becomes the limiting factor. Thus, the crack growth in the environment is equivalent to in air. This happens at the intersection points of the air and methanol curve in the plot. The plasticization factor, beta, which is the ratio between the average G methanol and G air for both polymers, can be found. So the smaller the value, the greater the environmental effect it has on the polymer. So here is a summary table of the critical initiation time and crack speed with its corresponding G value. The results show that BOPMMA has a greater resistance to ESC than amorphous PMMA. This is probably due to the aligned polymer chain of BMMA having less free volume and hence a lower flow velocity within the polymer. Both critical crack speed and critical crack propagation energy have increased 2 orders of magnitude from its amorphous to biaxial orientated structure. And you can see from the plasticization factor, methanol has a greater impact on amorphous PMMA. Here we have the SEM images for in-air specimens. On the left is amorphous PMMA, and on the right is biaxial orientated PMMA. Both images were taken near the relaxation control region with crack growing downwards. In comparison, the biaxial orientation has resulted a rougher fracture surface compared to the amorphous specimen. This suggests that the effect of crazing is more dominant in biaxial orientated PMMA. And here we have the images for both polymers in methanol. The SEM image from BO-PMMA have shown a high alignment along the direction of crack growth, which may suggest a high degree of polymer chain alignment from the stretching process, and appears to be significantly rougher in comparison to the amorphous PMMA, which agrees closely and is reflected by the increase in fracture energy required for crack initiation and propagation during ESC, as more energy is required to generate a larger, i.e. a rougher fracture surface. And here we have the conclusions. The biaxial stretching process results in an increase in polymer chain alignment. The BO-PMMA has less free volume and lower flow velocity within the structure, hence a greater resistance to crazing in methanol. The increase in fracture energy shows good agreement with the rougher fracture surfaces associated with the biaxial effect. The resultant microstructure of the biaxially orientated PMMA benefits an improvement of the overall material fracture properties in the direction of stretch. The critical crack speed, critical crack propagation energy, and the plasticization factor have greatly increased from the amorphous state. And lastly, BO-PMMA has a greater resistance to ESC for the in-air and in methanol environment, hence a longer component life expectancy than the amorphous PMMA. Thank you.